So this one, we've got if x is normal 185/15 squared, sample of 25, mean of 179, test at the 5% whether the mean has fallen. Fallen means it's a one-tailed test. We're interested in a less than here for h1. One-tailed 5%. That would launch me into this diagram over here. 5% down here, my critical value. I've written down my distribution of x, my sample size, my distribution of x bar, which is sigma squared over n at that point, which I think works out to be 9 for my variance. So then you're interested in working out the critical value. Well, that's finding the probability that x bar is less than that critical value is 5%. That's when you go into your phi of the value, take away the mean over the standard deviation equals 5%. Anti-phi-ing, you will get familiar with this minus 1.645 or plus 1.645 for 5% either side. Rearrange it, get a critical value 180.065. So there's your critical value, there's your mean. Your observed mean is over here in the tail, so you reject h0, therefore you accept h1 and state at the 5% significance level we conclude that the mean has fallen below 185. Now, fourth example, it takes on average 21.75 seconds for a lab rat to complete a task. Placed in a different environment, a random sample of 50 times taken to complete the task was recorded and summarised as sigma t equals 1107 and sigma t squared is 24,000 and something. Test at the 5% level whether the new environment has changed the mean time to complete the task. Right, first observation in this question compared with the other three we've looked at.
We're not given we're given data to figure out what the distribution is.
We don't have any population information here. So here we have no values for mu or sigma squared. The great god of statistics has not been as helpful today to us. However, we can plod on because what will we use? Sample, and from that sample we will calculate mu hat, which is an example of an unbiased estimator. Exactly, yeah. Okay, good. So we will have to use unbiased estimators.
Don't we have mu? It says 21.
We can get mu and the variance from those results.
Well, yes, okay. I take. Okay. So yeah, we have to use an unbiased estimator for one of them. I take your point. Yes, you're quite right. Okay. So we have two. That was supposed to be no, wasn't it? There. I said we have no values. That's supposed to say. So we have no value for sigma squared, certainly. Okay. But we yes, we do have mu after all. Yeah. Okay. So anyway, step 1, h0 and h1. So test at the 5% whether it has changed the mean time. So h0 is mu equals what it says, 21.75 seconds. h1, what will h1 be?
Equal to, it's two-tailed.
Yes, not equal to, just has it changed? So it could go up or down, they're not bothered. Is not equal to 21.75 seconds, so it's a two-tail test. And our significance level is given to us as 5%. Okay, so cue a drawing. We've got a mean of 21.75. We've got a two-tail test. 5% split between each tail, so there's 0.025 as a decimal in each tail. And I will need to find one of two critical values, a lower critical value and an upper critical value, one for each tail. So this is all to do with T, or T bar, because we are looking at the sample information. So yeah, we don't know sigma squared, okay? So we have no sigma squared, so we use our unbiased estimator. Sigma squared hat. What is sigma squared hat? From this morning's lesson. Can you go I'm looking for the other bit first of all. n over n minus 1 times by s squared, where s squared is the sample variance. Yeah. And how do I find the sample variance? What's my formula for the sample variance? And using the summary statistics that I am given, sigma t squared and sigma t. That's, yeah, because that's the mean squared. Okay, so yeah, the sum of the squares divided by n, take away the mean squared, because that sigma t over n is t bar. So sigma t squared, we are told, is 24,592.35. N is 50. Bung the numbers in, and you will get out s squared. If anybody has an s squared, shout it out.
1.6674.
That is what I have here. Good. Always reassures me if somebody agrees. So, sigma squared hat, our unbiased estimator for sigma squared, will be n, which is 50, over n minus 1, which is 49, times by that value, which will increase it by a little bit. What will it increase it to? 1.701. Yeah, that's right. Okay. So I've got that t bar is going to be normally distributed 21.75, that was given to us, and 1.701. Is that correct? Good, yeah. This over here should be sigma squared over n. So don't forget that. I know you've done some 50 stuff up here, but don't forget that. So that bit in there is sigma squared hat over n. Don't forget the n down there, which is a mistake that some people can make sometimes. So don't forget this n down here. And now it's just like the questions we've pretty much been doing. So we were given a sample mean of, well, we haven't actually worked out a sample mean, t bar. T bar was this 1107 over 50, which should be 22.14. So that's our test statistic. That came from sigma t over n. So on my diagram, I'm just going to shoot up to my diagram a minute. That is above the mean, so it's C2, my upper critical value that I'm going to be interested in here. So if you guys want to have a go from here. You'll want to turn it greater than into a less than. And the anti-5 value you will come up with is another one that you will just get in your head. What anti-5 value are people going to be using here? 1.96. Yeah, and again, that's at the bottom of the tables. Okay, for the 2.5% one. So it's a case of solving this equation here. Has anybody got a value of C2 yet? You're working very fast, yeah. 22.112. cue me a new drawing. So, I've got my critical value, 22.12, which is here. My test statistic is 22.14, which is higher. So my test statistic is in my critical region. Just checking, what do I do for that? Reject the null hypothesis, yeah, that's right. Okay. And then go back and look at the context of the question and write down a sentence. So I'm concluding at the 5% level, significance level, we conclude the average time taken by the lab rats has changed and is no longer 21.75 seconds.